So, okay, so back to I will this. So it's the last time. Okay, so the last lecture about different types of structures and certain basic aspects of structures. And we continue with the basic aspects of this particular class as well. Okay. So, the class left is studied about structure. We can say AX study or AX to study. That's the first. This kind of book is began as a word of now, aside what factors that decide uh,
Hello.
yeah.
Ma'am, your voice is not audible.
Okay, let me just try. Is it okay now? Maybe you can type in. Is it okay now? Am I audible?
Yes, ma'am. Yes, ma'am. Now, okay.
Okay. Okay, fine then. Yeah. Okay, so what I was saying that normally when we say this material adopts the rock soil structure or this material adopts the zinc blende structure or a woodside structure, then what are the factors that control this? That what structure would be adopted by material? Normally, there are very specific fields that deal with this kind of let's say science, but we would discuss what are the general factors that would decide what crystal structure your compound could adopt. Okay. Now, the first and the foremost thing is formula of the compound, by which I mean the stoichiometry of the compound. Okay. That means if your structure has the formula AB or AX, it can adopt only AX kind of structure. It cannot go to AX2. Okay. Now, there would be certain, let's say, exceptions, but we would talk about the generalized understanding about how to determine if I'm given a chemical compound, then what could be my guidelines on what structure your material would adopt. So first one is stoichiometry. Okay, if whether it is 1:1 or 1:2 or 1:3 and so on. Second thing, whether the bonding is ionic or covalent. We'll discuss about this a little more in the next slide because this is also very essential to what crystal structure would be adopted by material. And third, which is again, if we don't really take it as, okay, we are studying this, it's a very common sense kind of thing, the size of the atoms and ions that are involved, okay, because ultimately they are getting packed. So not just their sizes, but also what is their relative sizes. If you remember in the last class, we also described structure as this would be packing of this ion and these ion will occupy these voids. Now the size of the void depend upon the size of the ion that does the packing. CCP, HCP, or there are many intermediate packings also, which we have not discussed about. So, not just sizes, I would repeat, even the relative sizes. Okay. So, in fact, there are few structures wherein even if your relative sizes of ions are equal, let's say something called AB and then you have CD, but the ratio of A and B is also equal to C and D, but C and D are the larger larger ions, while A and B are smaller. Even that affects the crystal structure. That is why I mentioned the third point, that is absolute size of atoms and ions, and also their relative size. So four factors, there are many other factors, of course, But these are the ones that contribute majorly to deciding what would be the crystal structure of your nominal compound, the compound that you're looking at. Stoichiometry, the bonding, which means ionic, covalent, or metallic, the size of atoms and ions, and not just their absolute size, but also the relative sizes. Okay, which is also very commonly known as radius ratio rules, and we'll talk about it. Okay, now this is again a general thing that deals with the stoichiometry. What do we understand? If the formula of the compound is, let's say, AXBY, then it's very natural to understand that the coordination. Okay, now these are the things. See, all these guidelines, what they help you in. You do single crystal XRD, or you do, whatever XRD you want, or Newton diffraction. Now they give you certain sort of patterns which help you to determine the crystal structure. Crystallography, which Dr. Kanubarik will take on in the next module. But the thing is, in the earlier times, when you have got these patterns, many a times, if you do not really know anything about the compound, let's say it's a new compound altogether, then you need certain specialized softwares to help you solve it. Okay. So when softwares were not there at that time, these were the guidelines that would give the scientist an idea about what could be the coordination number, what could be the stoichiometry, what could be the voids that they would be occupying. And that is why these factors become very important even now. So as I was just saying, that if the formula of the compound is like AXBY, then the coordination number will be in the ratio of Y:X. Okay. Now here the condition is that in this structure, A is bonded to B and B is bonded to A. So direct AA or BB contacts do not occur, then this particular condition applies. Okay. For example, if you have a compound AB2, now what is this? This is your fluoride structure. CaF2. The coordination number will be in the ratio 2:1. Like if you go back to your coordination CaF2 structure, if you do not really recall it now, I would tell you that calcium was making the lattice and its coordination number was 8, and fluorine was in the tetrahedral hole, so its coordination number was 4. So basically CaF2. Now your X is 1 and your Y is 2. So the coordination number of ratio of the coordination number of calcium and fluorine is 2:1, and here we have 8:4. Okay. So I hope this is clear. Now suppose you have a ternary compound, right? Many a times these kind of things are seen. In the next class we'll study about the structure of pyrethroids, A2B2O7, or perovskites, AbO3. They have more than 2 ions. Then what is the ratio? In that case, this is the rule that is followed. If your formula is AX, BY, and CZ, then X into coordination number of A plus Y into coordination number of B is equal to Z into coordination number of C. We are assuming here C is your anion, let's say oxide ion. Okay. And this is actually derivable from this particular thing only. So if you go and do about it, a very, very generalized thing of how an idea of, now see, here we talked about that the ratio would be this. We still do not know what would exact coordination number would be. So that we can find out by radius ratio rules, and we'll go to them in a while. Nature of bonding. How does nature of bonding suggest a guideline for structure? Now what happens is your covalent bond, if your molecule or the compound that you're looking at, the bonds are relatively more covalent. Covalent means there is a sharing of electron pair. Now, when there is a sharing of electron pair, the electrons are concentrated between the two atoms. What does it mean? The bonds are directional. Okay, bonds are directional, and the atoms have generally very preferred coordination environment. It doesn't depend upon what is the counter cation, anion or the other cation, and the coordination numbers are relatively small. Okay? But in case of ionic compound, what happens is ionic solid, when there are ions in the structure, they tend to have as much attraction as possible. Okay, because that provides the stability. Now, because the ground is not between iron and so they tend to have maximum attraction. So what happens is maximum attraction. It's a concentrating on one at this point. On the way at this point of opposite charge around it. So what does it mean? It maximize its correlation. Now how that what would be the most number that we have as number that we take it up maximum number of the ions and then just around it. So now it's not only it's a first way, it's actually the
Ma'am, you are inaudible again.
okay now. Okay now. Sanjay?
No, madam.
Hello, ma'am. No, ma'am, it's still static.
You are not
A lot of
audible.
static.
That was static. Okay. Everybody facing the same problem?
Yes,
Anybody
ma'am.
else, please? Okay. Like, what is it, Dargavan? There's a break in the voice sound, or you're not able to hear it at all?
No, ma'am. Actually, break into the voice.
Okay. So maybe we try reconnecting again.
Yeah, ma'am. That will be fine.
Okay. So let me just talk to our IT person here. I just have one request. People who are on YouTube, are they also facing the same issue of the break in the sound? Can you please put it in the chat box?
Ma'am, the YouTube feed is being fed by the WebEx Cisco API, so it also has the same audio.
Is it Parniti? This will be the case.
It is audible on YouTube.
Actually, he is parallelly our IT help. He's parallelly on YouTube. He says it's pretty audible there. So I don't know what to do. Maybe I mute again because we cannot probably. What he tells me that I cannot close this because once we do, then we'll have to send you another link.
Now it is audible, ma'am.
Is it? So what we do is, I think, Parniti, you be on chat side by side. So wherever you feel there is a problem, just type in immediately, okay? So that I know that this is what I have to repeat, okay?
Okay, ma'am.
Okay. So I don't know how much of it we have to go to lecture to Parniti. So you be on the chat box also, side by side. You just type in that you were clear when I told you that covalent solids have got directional bond and smaller coordination number.
Ma'am, the last properly clear thing was when you were explaining the ratio of coordination numbers.
The ratio of coordination number. So the second slide has not been very audible, right?
Yeah, this particular slide has not been that audible.
The nature of bonding. Okay, so what I'll do is maybe can we keep only one of them on the unmute this thing so that immediately the person can tell you. Okay? So we are keeping a Sanchit on unmute.
He
Okay,
can
so
unmute on his own.
okay, so you can unmute. So just tell me wherever I go inaudible. Okay. Hello.
Yeah, sure, ma'am.
Okay, nice. So sorry for all these disturbances, but I guess we have to live with this. Okay, so what I was trying to say is how the nature of bonding affects a crystal structure. So I was trying to tell you that when you have a compound wherein the covalent character of the bond is more prominent. Now, what is a covalent bond? Okay, it is a sharing of electron between two atoms. Now, the entire electron density lies between the two atoms, which means the bond is directional. Also, irrespective of what the counter cation's preference is, this particular atom will have its own coordination preference when it is forming a covalent bond. So the result of all this is that covalent solids have got very directional bond, and also the coordination number is smaller for them. And they tend to adopt a structure where coordination numbers are not very large. In case of ionic solid, now the story is totally different. Why? Because they are ions. Okay. The whole way for them to attain stability is to maximize the attraction between the unlike ions and minimize the repulsion between the like ions. So this force of attraction and repulsion, it doesn't really happen between only the pair of ions, unlike the covalent bond. It actually is almost wherever around the more than one layer, the second layer, till it operates. So the result is, because it wants to maximize the attraction, if I'm concentrated on a particular ion, it will try to accommodate as many unlike ion as possible around it. Okay. So the result is that it will tend to adopt as high coordination number as possible. But there is a limit to it. Now, what is that limit? That will read in the study in the radius ratio rule. The entire, let's say, the conclusion from this is that ionic solids, they tend to have more symmetrical structure, wherein the coordination number of both cations and anions are as high as possible. And the only reason behind is that they want to maximize the electrostatic force of attraction. Okay, so just giving you an example. Now consider these three: barium oxide, strontium oxide, mercuric oxide. Now what we talked about, that as long as their stoichiometry is different, they should have similar crystal structure. In that case, they should have similar crystal structure. But barium oxide and strontium oxides are ionic solids. Okay, so they adopt the rock salt structure, which is the NaCl kind of structure. And we studied in last class that the coordination number is 6:6. Now, if we consider the fact that they are both AX, also on the basis of their radius, like mercury as compared to barium or strontium, even based on that particular criteria, mercuric oxide should also have been rock salt. But the thing is, this particular atom, it tends to form more covalent bond. So the crystal structure, the ultimate crystal structure of mercuric oxide, it has something of the linear arrangement of OHGO. Okay, OHGO. So the coordination number is much smaller than what is possible in the rock salt structure. Second example, if you consider aluminium, the halides of aluminium, AlF3, AlCl3, Br3, and triiodide. The covalent character increases along the series. So this is most ionic and this is most covalent. Now, how does the structure changes? AlF3 is a high melting ionic solid. Okay, don't go on the structure. We'll talk about the structure in the next class. AlCl3 is part ionic, part covalent. So it forms a layered structure, CdCl2 type. So within one layer, it is high coordination number. Then the second layer is empty, and third layer again high coordination number. So part ionic, part covalent, and hence it forms layered structure. When you move to this two, okay, so it has a molecular structure. What I want to say with this is Al2Br6, the structure is loosely based on hexagonal close packing of bromine. So these bonds are all bromine ions, wherein your aluminium occupies a tetrahedral group. But if you see it doesn't really form the same structure as your nickel arsenide or woodsite, wherein all the atoms were bonded by the atoms which were coordinating it. So it is like this: a molecule of Al2Br6, and this molecule is loosely bound to another molecule. So it is based on HCP, but it is a molecular structure. So if you try to kind of, then this is the structure of the molecule. How you can see it in this particular structure is, now this is the 1, 2, 3 are the bromine ions in the bottom layer, and 4, 5, and 6, the dotted ones, are the bromine ions in the second layer. Now, aluminium is occupying the tetrahedral wall between these two. Okay. Now, if you want to join, see it in this form, your 1 and 2, okay, they are bonded to 5, which is here, and 3, which is bottom. And 5 and 3 are bonded to 4 and 6. So, 3 and 5 are the bridging ones. So this is the molecule of Al2Br6, loosely based on the hexagonal close packing of bromine, aluminium occupying the tetrahedral. So that is how the covalency from AlF3 to AlI3 can vary the structure, despite the fact they are all with aluminium, despite the fact they are all halides. Okay, now effect of sizes. What could be the effect of size? And we are talking of, let's say, for covalent solid, normally size does not really make a lot of effect, because as I told you, it is controlled by valency and bonding requirement. And for covalent solids, the elements generally have their preferred coordination number. But for ionic solid, because an ion, let's say a cation, would try to accommodate as many ions as possible. But the thing is, it cannot really keep on increasing the numbers around it. So that is why larger the cation, more will be the anions that it can accommodate around it, and larger could be the coordination number, because it will maximize the attraction. Okay. Now, why are these structures symmetrical, ionic solid, preferably more symmetrical? These are the two factors that control it. One is they will try to accommodate as many as possible. But the thing is, now if you realize your atoms have got a nucleus and an electronic cloud, if you try to just keep on dumping one after other, at some point the repulsion between the electron clouds will happen. So they will tend to be far apart. So the fact that more the number of ions will maximize attraction will keep on increasing. The fact that after a particular number, this will tend to increase the repulsion, it will try to keep it in check. So they will be separated out in the space in the most symmetrical manner that is possible. And how many ions we can accommodate? Of course, it depends upon the size. That is why size is an important criteria. Okay. So again, this is the same thing that I was just saying. Coordination number is determined largely by electrostatic attraction. Cations tend to be surrounded by as many anions as possible, and vice versa. It maximizes attraction and it maximizes lattice energy. Lattice energy would be the last topic of today's lecture. What is a lattice energy? Even if you don't remember the definition, how nicely and strongly your lattice is put together, that determines its lattice energy. How difficult it is to break it, that is the lattice energy. Okay. So more attraction, more strength of the bond, and maximization of lattice energy. Now, radius ratio rule. We said a cation will try to accommodate as many anions, but how many will it be able to accommodate at all? There has to be some factor which should decide it. That is the cationic size, not just the cationic size. Relatively, what is its size relative to the anion? Okay, a smaller cation can probably accommodate 6 smaller anions around it, but it will be able to accommodate, let's say, only 4 larger ions. So it depends upon the radius ratio rule. So what is the importance of radius ratio rule? They give you a guideline about the coordination number that is possible for a particular set of cation and anion. And for a crystal structure, determining the coordination number is one of the most important factors. Okay. Now, what is the rule? So what it says is, we'll just in the next slide, we'll talk about what could be the ratio that decides what should be the coordination number. There's one thing that I would like to talk about, okay? If you have, now this is the most ideal situation, wherein your cation is at the center, anions are surrounding it and touching it, and cation is also touching the anions, okay? Now let's say cations start getting a little bigger. Somewhere you will reach this situation where cation is touching all the anions, but now anions are not touching each other. This is also stable. But a situation like this, where your anion is small, not touching the anions are touching. Now, what do we call this situation? Is cation is actually rattling in the hole. It is smaller than the space that is provided. This situation is highly unstable. Okay. And when you reach this situation, the coordination number for this particular pair of cation and anion would be lesser than 4. Okay. Similarly, in this direction, as the cation would keep on increasing for the same anion, ultimately a situation would reach when it would tend to adopt the higher coordination number. That is what sets the guideline on what could be the boundary line for a pair of cation and anion regarding the coordination number they can adopt. Okay, so now these are the different radius ratios. So let's say you start with cubic. There is a cation, it can accommodate 8 and 9. If the radius ratio, when we say radius ratio, it is always R cation. Normally it is smaller ion by bigger ion. Okay, but in general, we know that cations are smaller, so it is defined as RC by RA or R cation by R anion. When it is 1, a cation can easily accommodate 8 anions around it. Okay, then the ratio start decreasing means now your anionic size has started increasing. Anionic size has started increasing or the cationic size has started decreasing. So at some point, what will happen? That it will not be able to accommodate 8 because it is becoming smaller. So the radius ratio will reduce to 6. And at what point it will happen? At RC by RA is equal to 0.732. And when I tell you this, and we will discuss about it later also, these are not hard and fast, but these are only the general guidelines. Like 0.732, I mean, you can never really expect, right, that the ratio of cation and anion to third place of decimal. But these have come from the geometrical consideration and these are also found to be true. Okay. Now again, the cation keep on becoming smaller till 0.414. It will sustain 6-fold. Beyond that, it will go to tetrahedral because now it cannot really take 6 ions around it. Then this will persist till 0.225. Beyond that, it can accommodate only 3 anions, right? And after that, it is the linear arrangement. One thing that I would like to bring to your notice is, did you notice that coordination number 5 is absent and coordination number 7 is absent? We directly jump from 8 to 6 to 4 and then, 3. Okay. The reason is, when you have coordination number of 5, it is okay to, let's say, when you say 5, the anion is somewhere in the center. Okay. So it is possible to have these 5 as equal. But with pentagons, you cannot, if you see the pentagon, let's say, the tiles, if you take the pentagon tiles, you cannot fill up the entire space. You will always have this empty spaces. Okay. If you basically try to make a distorted pentagon, some bonds are longer, some are smaller, then it is possible to make space filling polyhedra with pentagon. But where you have all the cation and anion bond lengths are constant, the pentagons are regular, it is very difficult to, it is not possible to fill in the entire space with coordination number 5 and 7. So in 2D, You can have 5-fold and 7-fold symmetry, like they can be the point symmetry, but they will never be the space symmetry of the system. Okay, so I hope that is one very interesting point that I feel happy about teaching the students, and I'm sure it was a new learning for you. Okay, now this is simply the affirmation of how these are the experimentally determined coordination number, these are the calculated radius ratio, and these are the anticipated. Okay, fine. Now, what are the limitations of the radius ratio? Are they valid always? Most of the time, yes, but they are also, there are exceptions. What could be the reason that they fail sometimes? First and foremost, these radius ratio rule, they assume that your cation and anion are hard pairs, which is never the case, right? And because they assume hard pair, they assume that they will have a particular fixed radius. But that's not possible. Okay. Second, the ionic radii, how are the ionic radii calculated? So basically from single crystal X-ray diffraction, we get electron density maps, okay? And from electron density map, we see, okay, that this atom has one particular electron density, like here it is maximum, so that should be nucleus, then it is minimum, so that should be the boundary. But the fact is, these densities, they also do not have a very, let's say, hard and fast cutoff. It's only that it decreases at some point, and there we assume, okay, this is the radius. So the ionic radius, and there are various ways by which you can determine ionic radius. So ionic radius, themselves they vary depending upon how you have calculated it. Which source have you taken it from? So now these are the factors you are actually using to calculate your radius ratio. If your ionic radius itself is not, it's kind of, it has an error margin, then obviously the radius ratio will falter sometime, because getting a good radius ratio is the backbone of radius ratio rule. Thirdly, your ionic solids will never be completely ionic. There will be some degree of covalency. Means, again, you will never be sure of the radius that you are taking. That if there is some degree of covalency, means there will be overlap. So whatever ionic radius you've got out of it is definitely not the true picture. Thirdly, and most important thing is this thing. Okay, what about the borderline cases? Okay, we talked about these radius ratios: 0.1, 0.732, 0.414, 0.225, 0.155. What happens if your radius ratio is, let's say, 0.42 or 43 or 0.40 or 0.39? In that case, what happens is your same ion will, these are the cases wherein we observe polymorphism. Polymorphism means this particular pair of cation and anion can make 2-3 types of crystal structure. Because for them, it is possible to have more than one coordination number. Different coordination number means different kind of crystal structure is possible. So here, let's say your germanium oxide, it exhibits both silica-like structure where the coordination number is 4, and butyl structure, that is TiO2 structure, where coordination number is 6. Okay. For ZrO2, the predicted radius ratio is 0.68. Now, if you go here, 0.68 means you are here, right? So it predicts the coordination number of 6. But it is kind of borderline because it is close to 0.73. So your zirconia actually exists in 3 polymorphs: monoclinic and tetragonal and okay. So what are the different exceptions? What are the limitations of radius ratio to be studied? It applies only to ionic solid, and also it applies only to AX type of solid. Okay. Ionic radii themselves they vary upon the source, so radius ratio are just the guidelines because you do not really have a fixed ionic radii. And ionic radii, the other thing is they are themselves the function of coordination number. Suppose your ion has coordination number of 8 and cesium fluoride type of structure, and You increase the pressure, it adopts NaCl kind of structure. So 8 and 6. So if you calculate the ionic radii from this structure, it will be larger as compared to this when it will be smaller. So ionic radii themselves are the number of coordination numbers. It's kind of chicken and egg situation sometimes. And as I said, most important exception come when you have borderline radius ratio, because then there is a possibility of adopting more than one coordination number as per the radius ratio rule. Okay, now this I have jotted down just for the clarity how the radius ratio were calculated. We read about certain fixed number. How did those number came about? Here in the slides, okay, one more thing, the slides would be shared with you after this lecture today for both lecture 1 and lecture 2. So you can go and have a look by yourself. And I've given it for all the coordination number, but I'll discuss it only for one so that we save time. This is simple high school geometry. Okay, so when I'm talking about coordination number 3, the smaller is the cation in between, and these are the anions that are surrounding the cation in a triangular fashion. Now, what happens is, if you can see, this is an equilateral triangle. So AB is equal to BC is equal to AC. And if I am assuming that the radius of anion is R minus and radius of cation is R plus, then your AB is equal to 2R minus. Okay. Similarly, AC would be 2R minus and BC would be 2R minus. Whereas BD, now there is a small cation at point D, BD is R plus R minus. Okay. Now angle ABC is 60 degree. So angle DBE is 30 degree. So by trigonometry, cos 30 is, this is 30. Okay. Cos 30 is BE by your perpendicular D, that is BD. Okay. Now, which means BD is equal to BE by cos theta. What is BD? It is R plus R minus, that is equal to R minus by cos theta. And by simple maths, you reach this value. R plus by R minus is equal to 0.55. Very simple. You simply have to start here correctly. Okay. Triangular arrangement, draw an equilateral triangle, place the cation at the center, find the relation between R plus and R minus using a trigonometric formula, and you will approach here this formula. So what it suggests is, when your anions, like this is the ideal situation, when your anions are touching each other and the cation. Okay. Similarly, for coordination number 4, we assume a tetrahedra, but for calculation purpose, we are assuming one triangular face. Now, this is the atom at the top, and these two are the two of the three that are forming the basal plane of tetrahedron. Okay, and this is for the coordination number 6. And here we are assuming because all the bonds are equal, unlike tetrahedra, we are assuming the square in the center. Because this is your octahedra, cation at the center, one up, one down. I am taking these 4 circles. Okay. If you have any problem in this, it's a simple geometry. You're very welcome to come back to me in next class, and we'll get back to this slide. Okay. Now another point that I want to discuss is lattice energy. What is lattice energy? I told you in a very crude form. How much energy do you need to break that crystal? More is the lattice energy, stronger is the crystal. So if we talk in technical terms, net potential energy of an arrangement of charges that form crystal structure. The crystal structure has certain specific arrangement of charges, positive and negative charges. So over the crystal, what is the net potential energy? That is your lattice energy. And numerically, how do we say? We say it is equivalent to, now we're talking about molar, per mole, equivalent to sublime the crystal. Sublime means evaporated and then break it into gaseous ions. It is equivalent to sublime the crystal into gaseous ion per mole. For example, NaCl solid, let's say I have 1 mole of NaCl solid, the energy that I require to break into gaseous sodium, gaseous fluid. So now, even if you have not studied anything about lattice energy, if I ask you what will it depend upon, you will first tell me it will depend upon charges. Higher the charges, more will be the force of attraction, higher would be the lattice energy, right? Second factor, internuclear separation. Closer are the opposite charges, more is the attraction, right? Third is crystal structure, because crystal structure determines how those charges are arranged. So the three factors that control your lattice energy are crystal structure, charges of the ion, and internuclear separation. Okay, now why I love doing the expression for lattice energy, because it kind of clarifies the concept how the lattice energy will depend upon three factors that we just discussed. Okay, so we'll take only 5 to 7 minutes and be with me. So in principle, whatever that we discussed right till now, what could be lattice energy? Lattice energy depends upon the forces between the ion. What are the two different type of forces that would be present? Attractive force between the unlike ions, repulsive force between the like ions. And whatever would be the net energy would actually be the compromise or the summation of these two forces. Now one will have positive charge, these two potential energy due to repulsion and due to attraction. Now potential energy is negative when we are talking about attraction. Potential energy is positive when we are talking about repulsion. So if you remember your basic physics, the potential energy when you have two charged ions, Z plus and Z minus, separated by a distance R naught, potential energy is given by, this is a basic formula, just remember this, Z plus into Z minus divided by R naught, and this constant E squared by 4 pi epsilon naught. This is the charge on electron, and this is the current. Okay. So how will we calculate this? We'll take any particular structure. We'll take rock salt. That is a favorite of solid state chemists mostly. They'll concentrate on only one ion and see how many attraction and repulsion are present around it. And then we will scale it up to the n number of ion or one mole of ions. Okay. Now this is your NaCl. Okay, I will revise NaCl with you for one more time so that you understand the lattice energy. Here I am assuming my now NaCl is FCC of one ion, where the octahedral holes are occupied by second ion. Now FCC of one ion means, let's say, assume an ion. Now an ion is present on the corners and center of all six faces. And sodium ion is present in the octahedral group. And as we studied yesterday, in a cube, where are the octahedral holes present? Okay, I wish you do all these things side by side. The octahedral holes are on the edge centers and body center. Okay, so these are the places of sodium. Now you be with me and let us concentrate on this center sodium. Okay, this particular sodium. What are the nearest chloride present to this sodium? This sodium is in the octahedral hole, remember? So it has to have 6 chlorine. What are the 6?
Excuse me, ma'am.
Sorry?
I have a question.
Yeah.
Ma'am, whenever we see the example of NaCl, why do we always have 8 cells in it? Is this 8 cell thing the complete unit cell, or are we just trying to see the bigger picture?
No. This whenever you see this entire cube is the unit cell of NaCl. Okay. If you want to concentrate only 1/8 of that part, na, it will not be representing the symmetry of NaCl. सिर्फ वो एक 1/8 से आप पूरा NaCl का crystal recreate नहीं कर पाओगे. So that is not the unit cell. Your unit cell is the bigger cube. You are looking it at 8. Otherwise, it's not 8. Okay. Look at this cube. I'll draw it for you now. I say your chloride forms FCC packing. मतलब chloride आपका यहाँ है. ये corners पे है. Pardon me for it's difficult to hold the stylus for me. Okay. And also on the face centers. 1, 2. This is at the back. This is side, bottom. These are your chlorine. Now your sodium is at octahedral holes. इस सारे सेल में octahedral hole are at the body center, which is here. I'm drawing by cross, and the edge center. Okay, this way. So these are all sodium. Now you are looking it as 8 because they have only tried to join all the sodium and chlorine together. And why they have tried to join? So that in cell you are able to see what is the coordination number. That is why I'm saying I'm concentrating only on one sodium. Concentrate on the sodium at the body center. Okay. What are the nearest neighbor to this sodium? It has to be chloride. And it has to be 6. We know the coordination number is 6:6. Where are those 6? Okay. They have tried to join to make it more clear. This is first chloride. This is second chloride. This is third. This is fourth. This is fifth. And this is sixth. Can you see 6 chloride around this sodium? That is why they tried to join 1, 2, 3, 4, 5, and 6. Okay. So it has 6 chloride and they are how far away? Let's say I'm talking my bond distance is R0 at the distance of R0. Okay. Now what is the next circle of ion? That is how many sodium are surrounding this sodium? Of course, they are further from these chlorine, but where are they? There are 12 sodium surrounding this center sodium. Where are they? 1, 2, 3, 4. And then 5, 6, 7, 8, 9, 10, 11, 12. And at what distance are they? They are at the center of, okay, how do you calculate the distance of this sodium? Now I will try to use my cube because I've already. Give me a minute, please. Okay. Now you can consider this, right? Now you want to calculate the distance between these two sodiums. Okay. Now, if you just try to think about it, this is the phase diagonal. This is equal to the phase diagonal. Okay. Now, if your side of the phase, let's say how you can calculate it, it is this, consider this triangle. Okay. Now, this is equal to the side. So, okay, just concentrate on this. Now, this is your R0. This total will be by Pythagoras theorem. If you use this and this and this, it will be root 2 R0. This entire side. Then half of this, that is the distance between this sodium and this sodium, is root 2 by 2 R0. Or no, I'm somewhere making it wrong. I'll do let's do the phase center calculation nicely. Okay, this I'm trying to calculate. This is 2 R0. No, this is 1 R0. Yes, this is 2 R0. So what would be the phase diagonal? 4 R0 square plus 4 R0 square. Okay, so there will be 8 R0 square. And this is equal to your phase diagonal square. Just give me 1 minute. So phase diagonal would be 2 root 2 R0. Okay, yeah, fine. So we are right. I have to calculate the distance of this sodium from this sodium. Now this is almost equal to this and this, right? Okay, and what is this? This is phase diagonal. So if you think that this distance is R0, we already decided the distance between cation and anion, then this entire side becomes 2 R0. Okay, then this side is also 2 R0. If this is 2 R0, then this is 2 R0. This is 4 R0 square plus 4 R0 square will be equal to hypotenuse square. Then hypotenuse will be square root of 8 R0 square, which is 2 under root 2 R0 square. And I am talking only of half of this. So that is root 2 R naught. So there are 12 chloride at the distance of root 2 R naught. Then beyond that, we had sodium surrounded by 6 chloride, which were the nearest neighbor. Then 12 sodium were the next nearest neighbor. What would be the next nearest neighbor would be 8 chloride, which are at the corners of the cube. Now these are the next nearest neighbors. And these are at the distance of half the body diagonal, which is root 3 R. Okay, so forth and so on, we can actually calculate. I'm concentrating right now only on one sodium that is lying at the body center. What are then its nearest neighbor, the next nearest neighbor, the next neighbors, and so on. And this is how these are the atoms, number of ions, and these are the distances. Now, once I know this, I told you this formula. Okay. So, with these 6 chlorides, sodium will have the attractive energy. That would be minus Z plus Z minus pi R naught E square 4 pi epsilon naught into 6, because it was surrounded by 6 chloride. Second is there are 12 sodium at the distance of root 2 R naught. But now the potential energy is positive. That would be plus Z minus R naught E square by 4 pi epsilon naught into 12. Okay. Similarly, but now it is not R naught, now it is root 2 R naught. Okay. Then similarly, we can write for 8 chloride with root 3 R naught as a distance. Ultimately, we come with this expression. So this entire thing comes out. These factors will divided by these will come in the bracket. And this particular term is called M or Madelung's constant. Madelung's constant. Now, how did you reach on this value? By considering so many chloride were surrounding sodium, so many sodium were surrounding sodium, and so on. That depended upon what crystal structure do you actually have. So if there are two compounds which have same structure, their Madelung constant would be same. Okay, I hope this much is clear. Okay, so now this was only for one sodium. All right. Now suppose we talk about 1 mole of ion pairs. In that case, now I am representing this entire parenthesis value by m, and mz plus z minus pi r naught, this factor, and I multiply it by number of ion pairs, which is n. Okay. Now, till now we talked only about the forces between anion, cation, and all that. But irrespective of whether it is a pair of anion, or a pair of cation, or a pair of cation, they will have electron cloud. And those electron cloud, when they come together, they will repel each other. Now, this repulsion is different from whatever attraction repulsion we were talking about till now. Okay. That repulsive force is given by this particular expression. Now, this is a constant and this is a Born exponent having value between 5 and 10. Okay. Now, what will be the total potential energy? Sum of this plus this, and this is what is exactly done here. Now, like we do in all the things, we at R is equal to R naught. अगर आपके cation और anion और crystal structure वो stable है, that means उस particular point पे the potential energy is minimum. I'll repeat it. If your crystal structure is stable, for which you are trying to find lattice energy, it is stable. That is why you're finding lattice energy. The potential energy would be minimum, and if potential energy would be minimum, means the derivative would be 0. It will be somewhere here, so derivative here would be 0. So what we do is we have the expression of u, and we derive it, keeping it 0. We get something like this. You don't need to really remember this. I'm doing this because I want you to understand. Now, once we get this, we can calculate the value of b, because you will equate it to 0, and this is what b comes out to be. Now, again put b in this expression here for the energy, and you will get something like this. This is the formula of your lattice energy. That means your lattice energy depends upon number of moles, Madelung constant, charges on the ion. This is constant, this is constant. Distance between the ions, and this is constant. Okay. If I'm talking about, so what I said, your U, that is potential energy, or now we have actually calculated the lattice energy. It depends upon Madelung constant, number of mole, the equimolar distance, the distance between the ions, and the charges on ion. Now suppose if you have, we are talking about a particular crystal structure and we are trying to compare two compounds, let's say MgO and NaCl. For a particular ionic structure, both of them adopt rock salt. M would be equal because this is Madelung constant. We determined it by virtue of their position. Position if the crystal structure is same would be same. Okay. So now, and N of course, let's say we are determining molar heats, molar lattice energy. Then it will depend upon R, Z plus and Z minus. This is what we discussed in the beginning. It depends upon crystal structure, that is Madelung constant. It depends upon internuclear distance. It depends upon the charges. Okay. Now, how do we use this in practical application? For the same crystal structure, let's say I'm talking about rock salt. If your ions are divalent, then the product of divalent would be 2 into 2, 4 as compared to NaCl, 1 into 1, 1. The lattice energy would be 4 times than the compound with the monovalent. Okay. And visible here, NaCl and MgO, same structure, but the lattice energy of NaCl is minus 750 and MgO is roughly around 4000. Okay. Now suppose your Z are same. Let's say you're talking about NaCl and KCl. Okay. Same structure, same Z, 1, 1. Then higher the R, higher, like more is the distance between the ions, lesser is the lattice energy. And when the distance between the ions is more, when the ions are bigger. So if I'm talking about NaCl and KCl, Cl is same, okay, charges are same, but K is bigger than Na. So KCl will have lesser lattice energy as compared to NaCl. Then why, how does it help us? Because there's a direct correlation between lattice energy and melting point. There is a direct correlation between lattice energy and thermal expansion. Thermal expansion of solids are very important to the design engineers for any application. So, and what is the correlation between lattice energy and melting point? Higher the lattice energy means it is more difficult to break it, right? More difficult to break it means it is actually difficult to bring any disturbance. That means it will be difficult to melt it also. So higher lattice energy means higher melting point. Okay. So for the same structure, MgO, calcium oxide, barium oxide, same crystal structure, all are divalent ion, Mg2 plus O2 minus Ca2 plus Ba2 plus, all divalent, but barium oxide is bigger. So its R is bigger. R comes in the denominator, lattice energy is least. Lattice energy is least, and you can see the melting point is also least. So, and same as this is in the similar way, we can compare the melting point of MgO and calcium oxide. Okay, so this is what I wanted to discuss about the lattice energy. This was a short lecture. We'll start the second lecture in a few minutes. You can take a break, take, kind of calm down, and then we start the next lecture. So in this particular short section that we did, we studied about the factors that affect the crystal structure. We studied how the sizes and the related sizes they dictate the crystal structure, how bonding dictate the crystal structure, and also how the lattice energy is derived and what are the factors that the lattice energy depend on. Okay. I'll take 2 minutes break. You also take 2 minutes break. In the meanwhile, feel free to ask question now or later. All right. Audible? Am I audible? Okay. Thank you, Madhuri. So, in this particular next few slides, we'll talk about some of the important structures. So, whatever crystal structures we studied in the first lecture and half of the second lecture, or maybe the entirety of second lecture, what is simpler fundamental structure? Okay. Now, there are certain classes in materials. You would have heard about them, perovskites, which are also the nominal formula is AbO3, or pyrofluids, the nominal formula is A2B2O7, or the spinels, the nominal formula is AB2O4. Okay. Now, these are the compounds which have a little complex structure, not too complex once you know the concept of close packing in unit cell. But these are the compounds which are used in most of the functionalities. For example, all of you know that solar cells which are in market now are based upon silicon, but now there is an advanced version of solar cell which is being developed on perovskites. Okay, so you need to have the understanding of what the structure of perovskite is so that you can increase the efficiency, make them better. Okay, otherwise now, another example is if you know what ferroelectric, you know capacitors. Let's not talk of ferroelectric. Capacitors, they use of dielectric and ferroelectric material. And the most common ferroelectric material, which is, you know, let's say barium titanate, if you have heard of it. My teacher, when he taught me this, he told me that this is $1 billion compound. Okay. That particular material is also based upon, it's an AbO3 type of structure. Now, why do I need to study these kind of structures? I told you, if we know the structure, we'll know how the structure control the properties. Okay. If a material has particular properties and you know it has a particular structure, okay, and what do the solid state scientists do is they try to tune the structure and see how the property is getting varied. So what you are actually doing now is you are developing an understanding of what the crystal structure was, what was its property, what you have changed, how it has affected the property. So basically it has give you a knowledge about a key, which is your structure, to tune the ultimate output, that is your property. So this is nothing but it lays out the guideline for developing superior material for any application that you are looking at. Okay, so with this background, let us start. In this particular class, we'll talk about some of the crystal structure. If you be with me, they're very easy. And once you know them, you hardly forget them ever in life. Okay, so we'll start with perovskites. Perovskites, actually, this particular class itself is called perovskite, and it was named after the Russian mineralogist Lev Perovsky, but it was not discovered by him. It was discovered by a German mineralogist who was named Gustav Rose. Okay. Now, before coming to perovskite, I'll talk about the ReO3 structure. Very easy to remember. Nothing. I'll not even talk about close packing. Let me first explain you the structure. So, what ReO3 structure is? You have read about CCP. Okay. So, it is also nothing. If you let me talk about the perovskite, then I will come to this. So it's AbO3 structure. If you look it in the form of space filling polyhedra, it is, sorry, PO6 polyhedra. Now these are, if you can see these red buttons, which look like gems that the kids see, are oxygen. Okay, the red ones are oxygen. The yellow one is A, and inside the octahedra, if you can see the blue circle, they are B. So three-dimensionally, it is nothing but corner sharing BO6 octahedra. Okay, BO6, it has got 6 corners. It is joined to 6 more. It is sharing those 6 with 6 BO6 octahedra. They are further sharing to three-dimensional network of corner sharing BO6 octahedra, wherein between each of the a group of 8 BO6 as shown here, 1, 2, 3, 4, 5, 6, 7, 8, which is also called the cuboctahedral site, you have a cation. This is what perovskite ABO3 is. Now, in terms of unit cell, how would you want to understand it is, you first look at this, okay? Now, these are the color code. The yellow ones are the A's, the green ones are the B's, and the red ones are the red B. If you want to put, I will give you an option. Now, this particular unit cell can be described as A type or B type, but both are same. Believe me, whatever you choose, it is easy for you to remember, but in both ways we can define it. Okay. Now, A type is when you keep A at the body center of the tube. Okay. So keep A here. When you keep A at the body center, remember to keep all B's at the corners. Okay. The B's go at the corner. And then all the oxygen, they go at the edge center. It is as simple as that. Okay. This is your A type unit cell. I will repeat. If you are keeping A at the body center, just remember to keep B at the corners and oxygen at all the edge centers. Now, if I want to, let's say, whether we have done it right, whether it matches with the stoichiometry, let's count that. So, in one unit cell, how many A's are there? 1. How many B's are there? You have 8 green balls and they are at the corner. And remember, each corner is shared by 8. So 8 into 1 by 8, 1. How many oxygen? We have 12 edges, 12 oxygen. Each edge is shared between 4 cubes. That means to these 12 oxygens, 12 into 1 by 4 is 3. So what is the nominal formula that I've got? A, B, C. So we are working in the right direction. Now let's say you say, okay, no, I want to visualize a cell structure wherein I want to keep B at the center. It's nothing. It's the same thing. What you have done is you have taken this unit cell and tried to move your body center to this green. Okay, everything moves with that. Now, when you move with that, how does it look? Now you have concentrate on this B. You have brought this B in the center. When you have brought this B in the center, remember what we talked about here? It is all BO6 octahedra. So you have to make a BO6 octahedra. There's no escaping that. So how can you make BO6 octahedra? If your B is at the center, oxygens have to be at the face center. So you put B at the center. Once you have put B at the center, put A's at the corner and make an octahedra with the oxygen. As simple as that. If here we try to count it, 1B because it is at the body center, 1A because it is 8 of them at the 8 corners, and 3 O's because there are 6 of them at the face center, 6 into half, 3. ABO3. Easy to remember unit cell. If you want to keep A at the center, put B at the corners. If you want to keep B at the center, put A at the corners. But when you have A at the center, all the oxygens go at the edge center. But when you have B at the center, it will be easy for you to remember. If you remember, okay, I have to make a BO6 octahedra, so all oxygen goes on the face center. Okay, these are the unit cells of the ABO. Okay, again, the same thing. Now they also want you to know, okay, what are the coordinates? But we have already done that. So we know if I'm keeping A at the center, the B's are at the corner. Now here ABO3 that I'm looking at is strontium titanium. Okay, so your strontium is A. All right. Titanium is B. Now titanium is at the corner. Okay, so and there is only one lattice point, 8 into 1 by 8. So what is that lattice point? 0, 0, 0. Because normally I keep my origin at 0, 0. My corner at the origin is 0, 0. Now what is the coordinate of strontium? Easy, it is at the body center. So half, half, half. Okay. Now what is the coordinate of oxygen? You have 3 oxygens, 12 into 1 by 4. What are those? They are the edge center. So if this was your origin, it is half, 0, 0, Then you have 0, half 0 and 0, 0, half. Again, very simple. What are the coordination numbers? Let's work on that, right? Okay. Now, the coordination number of B, let's say first talk about B. Simple. We said that this structure is actually made by BO6 octahedra. So the coordination number of B, and now when you have more than 2 ions, we were talking about AB, AB2, there were only 2 ions. Now there are 3 ions, okay? Now when we talk of coordination number, we should also talk about what is the center ion that I'm talking about, and what I'm talking about, it is coordinated with what? So when I say the coordination number of AbO3, here I am talking about being coordinated by oxygen. So the coordination number of B is 6. It is 6 coordinated by oxygen. Coordination number of A is 12 by oxygen. How? Easy to see. Here A is at the center. You have 12 edges around it. So, and each edge has got oxygen at the center. So 12 are coordinated by oxygen. Okay. And how can I visualize this structure in space filling plane? We said it is BO6 octahedra sharing corners. When we talk about SRO12 cube octahedra, this site is called cube octahedral site. SRO8 cube octahedra, they are sharing faces with the SRO12 of the side, the cube that is lying on the side. So these are the two ways by which we can define the structure in terms of the space filling polyhedra. Okay. Now, why are we talking about this? As I told you, and this particular class is one class of compound wherein you name the property and you have it. Okay. Calcium titrate is dielectric, barium titrate is ferroelectric. Now these are relaxers, relaxer ferroelectric. I don't want to go into the detail, but they're highly upcoming and very useful material as energy storage capacitors, piezoelectric, semiconductor, superconductor. Okay, then protonic conductor, then even the magnetic material. So this particular class is very, very important for a solid state chemist as it shows a lot of properties. And the best part is this particular structure, I'll come back to it. Okay, now what I want to try to tell you here is we are talking about this structure. You know how much versatile this structure is? If I talk about barium titanate, okay, we know the oxidation state of barium is +2 and titanium is +4. Okay, so and oxygen is -2, so 3 into -2 is -6. So we have to have electron neutrality. Now because this is always 3, this is always going to be -6. This is one class of compound wherein you can have the cations +1 +5, +2 +4, +3 +3. So much elemental versatility is possible to be contained in this particular class, maintaining the same structure with different combination of charges. So what this shows is this is your periodic table, and the cations that are, the elements that are circled or put in a hexagon, all of them can actually occur in AbO3 structure at either A site or B site. That is the beauty of this particular class of compound. Okay, now, all right. So, give me a minute. RB plus RO and RB is here. This is equal to 2RB plus RO. So what this discusses is what two elements can form a AbO3 type of structure. That is defined by something that we call as tolerance factor. Now, this is something like the radius ratio rule, but in radius ratio rule we defined as R plus by R minus. Yahan pe it is a little complex. It is not as easy as R plus by R minus. It is defined as, this ratio is defined as Ra plus Ro, because now we are not talking about only one cation. We have two cations, A and B. Okay, that into that divided by root 2 of Rb plus Ro. This is called tolerance factor. Now, when this tolerance factor is 1, that is root 2 of Rb by Ro is equal to Ra plus Ro, you will get a cubic perovskite structure, which is this. Okay. Now, this, generally what happens is when you try to substitute some other element, let's say you have baryotite, you try to substitute some other element, your structure will break down or not take it. That is what I told you in the last slide, that this structure is very, very flexible. And how it is flexible, it will not break. It will try to adjust whatever you try to give it as most as it can. For example, in cubic, what I just described you, A is in the center. There are 6 TiO6 octahedra surrounding this. Okay. Now what happens is the tolerance factor become lesser than 1. Now lesser than 1 means numerator was Ra plus Ro. Now A is smaller, so small and smaller in respect that now it cannot fill this cavity. It will be smaller than what is the space provided to it, which means now it will rattle. What did I tell you a few minutes back was that if the cation rattles, it is not a stable situation. So what this structure does, it is so flexible that these TiO6 octahedra that are surrounding your A cation, they kind of tilt, like this will tilt inside, this will tilt inside, this will tilt inside, so that now they make the inside space smaller so as to fit in your A cation. Okay, so the structure remains, it is not broken down. But what has happened is the structure has now moved from cubic ABO to orthorhombic ABO. Okay, and what other changes have occurred? The coordination number of A has reduced from 12 to 8 because it has now become smaller now, so the structure is tried to accommodate it. Coordination number of B is still 6. So that is how ABO3 play. As you keep on decreasing the tolerance factor, it will keep on adopting different modification, retaining that ABO with reduction in symmetry. Okay, so that is how the size effect and perovskite. In fact, whatever experiments we do in ABO3, we try to substitute something in A, we try to take out something, we try to create a non-stoichiometry. We always keep in mind what is the tolerance factor of the resultant thing that I'm planning to do. Because it gives me some idea. Suppose I want to, I have ABO3, I want to replace some of the A by A prime and B by B prime. Okay, I know the radius, I can calculate the tolerance factor value. So even before I carry out the experiment, I will have an idea of what kind of structure would be possible here. So this is how we play with the perovskite chemistry. With this, I would want to stop here because I would not really want to, kind of stuff you in with the information. And next class, we'll talk about 2-3 more important structures. Then moving back to some of the properties. Okay. So with this, if you want to ask any question, I'll wait for 2-3 minutes. The slides would be available to you. Also, one very important information that our IT people wanted me to share with you is next class onward. This class, they're trying to be a little relaxed. But next class onwards, your attendance would be marked only if you log in between the first 15 minutes. Okay, so remember that. I hope you like the class and I hope that you'll come on time. And it's indeed a pleasure to teach you all. Feel free to ask any question, if not now, later on. After the end of 6 classes, I would be giving an assignment for you and you will be given some time, a week or 2 weeks, that we can decide, in which you will have to return that assignment to me. Okay. Okay, so if there are no more questions, we'll stop the class here. Thank you very much for being here with us, and I'll see you on Monday now. Okay, so happy weekend to all of you.